Welcome back to ECE 442-542. This is the lecture period before exam number 2. I think people are starting to have a little bit of a buzz about them relative to their participation in class because of exam 2 and maybe because of homework number 2, which is due today. Exam number 1, if you haven't yet signed up, if you're an online student, please make sure that you go through Examity if you're not using a proctor or if you're not coming on campus. You need to be signed up in advance to take your exam through Examity, and I think there's still some outstanding students, not outstanding in the respect of great, but outstanding meaning you haven't yet done what you need to do. So please make sure you do work on either signing up through Examity or obtaining a proctor for the exam, which is this Wednesday. There will be a review session, and hopefully no one will claim this room after our lecture today, and we'll hold the review session in this classroom. Hopefully that will work. The list of topics for the exam is on the exam 1 material website on D2L. And today what I want to do, prior to saying one more announcement, which is that if you need exam 1 material, I think you found it, some of you have, and started to look at what the practice exams might be suggesting the actual exam will look like for Wednesday's exam. We'll briefly talk about the process for exam number 1, and then we will go into the frequency response for a given discrete time systems transfer function, h of z. We'll do that by reviewing the continuous time case, then we'll finish the derivation of this transfer function for a low-pass filter, which we call h of z, and then we'll look at the frequency response, or how to find the frequency response in general for a discrete time transfer function h of z. And if we have time, we'll talk about the region of convergence, which really for homework number 2, the region of convergence is really just outside the largest pole's radius in the z-plane. And we'll get more into that, or it will become a little bit more clear when we want to go the other direction, when we maybe start with a transform expression and we need to go back into the time domain. That's when the region of convergence actually becomes a little bit more critical, to have that in addition to the transform itself. So we need the transform and the region of convergence to go back into finding a unique time domain expression. And we'll try to show that or illustrate that in a big picture sense, or really what are 3 region of convergence structures or shapes that are mainly what we will deal with. One is the entire z-plane with a circle cut out of it. That's the one that you probably have for most of homework number 2. The other one might actually be a disk, and the next one is a donut. Might as well talk about food since it's about that time of day. But the other one is an annular region, and we'll worry about how those regions of convergence are connected with the time domain waveforms if we have that opportunity, but that won't really be so much a part of exam number 1. Exam number 1, in terms of getting ready for that, what you need to bring to the exam is 1 sheet of your own notes, and that can be on the front and back of 1 sheet of paper, 8.5 by 11. You should bring in a z-transform table, and there's one on the D2L website, the course website. Calculator, they're basically computers, but this is what you're allowed. Don't bring in your laptop and expect to say, well, this is my calculator. Can I use the calculator on my phone? No, you cannot. So bring in a calculator, a separate calculator up to an 89, an Inspire, or an HP 51. And obviously you need to bring something to write with. What you can't have is a computer, a cell phone, textbooks, your neighbor, class notes. We'll try to spread out so that you do have room to perform on exam number 1. Any questions about the process for exam number 1? And we'll go through some of the topics that might be on exam number 1 during the review session tonight after this particular class. Okay, my eyes are still sort of working. Let's now talk about the frequency response. And when you hear frequency response, I think maybe what you should be thinking about is a Bode plot, or how does the magnitude and phase of a system vary, or what is its behavior as a function of frequency. And really what we're doing is that's telling us how our system responds to certain frequency excitations. We will now look at that maybe from a slightly different perspective, in that another way of thinking of that is to generate those magnitude and phase plots. We are really working in the complex S-plane just along the imaginary axis, and we're walking up that imaginary axis and we're saying, at this point, J1, what's this transfer function produce in terms of its magnitude and phase? And that's how that system would respond if they had a sinusoidal excitation applied to that system at a frequency of 1 radian per second. That's how the system would alter or adjust that sinusoid as it passed through the system. We've derived this relationship between S and Z, where Z is equal to e to the st, and that's just a unit advance. We maybe derived it for Z to the minus 1 equaling e to the minus st, which was a 1 sample period delay. But if we now replace Z with e to the st, and in fact also replace S with j omega, where we're interested in the frequency response, we will see that now instead of looking at h of z, we're looking at h of e to the j omega t, but if t is fixed, then we're really just varying theta, which we could say is omega t. What are we trying to communicate? Is this highlighted region in the 2 complex planes. I really have 2 complex planes sitting side by side. One is the S-plane. That's associated with continuous time systems. The right-hand complex plane is the Z-plane, and that's associated with discrete time systems. If we look at where this blue highlight would actually correspond to in the Z-plane, it actually corresponds to this unit circle between +1 all the way up to J and then back around to -1. We're now looking at evaluating h of z along that unit circle, half circle between +1 and -1 in the Z-plane if we wanted the transfer function or the frequency response behavior in the Z-plane. And what it's doing at a particular theta, you give me a theta, I can find that point on the unit circle. If theta was now pi over 4, we're now at an angle of 45 degrees at a radius of 1. And we would then evaluate our transfer function. How do the poles and zeros of this transfer function contribute to that particular point, h of j pi over 4? That's what we're trying to learn or better understand today. And to do that, let's review. That's what I'm hoping this is, the continuous time case. Meaning, if you're given a continuous time system, H of S, think of that as a filter, maybe a low-pass filter. That's what this transfer function could be. It could be a system. But for now, let's just view it as a filter. That's now H of S. What if I excite that filter or inject into that filter a particular sinusoid, where the sinusoid has an amplitude of A and a frequency of omega 1. That's my input time domain waveform. We have an amplitude of A and a frequency of omega 1. After the transients have disappeared, the output, if H of S is associated with a linear system, the output is going to be oscillating at exactly the same frequency that we started shaking it with. That's why we have this cosine of omega 1t. What happens is the amplitude gets scaled. How does it get scaled? It gets scaled by how that particular system performs at that specific frequency omega 1. And we want to know what's the magnitude of that transfer function, of that filter, at that frequency omega 1. In absolute terms, maybe that H of j omega 1 is 0.8. That now means that we scale A by 0.8. So we have 80% of what we injected in terms of our amplitude. So we had this sinusoidal signal, waveform A, and now coming out, the amplitude has been contracted by 80%. What else has happened? Well, it may have been delayed as it goes through that system, and that's what the phase, or the angle of H of j omega 1 represents. Now, if you lined the input waveform up with the output waveform, if the magnitude of H at omega 1 is 0.8, it's now collapsed or contracted by 80%, and it's now been shifted in time. So the peaks are not aligned in the input waveform and the output waveform. They're offset by this phase shift, which is introduced by the angle of H at j omega 1. And we can calculate that. If you have the transfer function, H of S, then you can find this magnitude and angle by simply evaluating H of S at S equal to j omega 1. That will just give you a complex number. If you substituted for S j omega 1, where let's say omega 1 is now 10, you evaluate H of S when S is equal to j10, and that will give you some complex number. That transfer function will just be a complex number at that particular j10. For any complex number, you can find its magnitude and you can find its angle, its polar form, and that's all that right-hand side represents. Its magnitude then scales the cosine at that frequency, and the angle shifts it in time. We could also compute that graphically, that information, the magnitude information and the phase information. And here I'm illustrating a generic case where I have 3 poles and 1 zero. It's a very busy S-plane, but for each singularity, for each pole and each zero, if I'm wanting to know how does each factor, each pole factor or each zero factor, how does it contribute to that transfer function at the frequency omega 1, you can now simply say, well, let me figure out what the hypotenuse is from that pole up to omega 1. What is that length? That's L sub P1 for the very first pole. How do I need to look at that location, j omega 1, what angle do I need to turn through if I start my angle at the positive real line facing to the right, and now I rotate, what's that angle, theta p sub 1? That's now the angle that that particular pole factor contributes in this collection of 3 poles and 1 0. And if you've drawn this accurately, you could actually pull out your protractor and your ruler and measure these lengths and angles and compute the complex number of that transfer function at a particular frequency, omega 1. The Bode plot is created by simply moving that omega 1 from DC, which is the origin, all the way up the imaginary axis to let omega 1 go off to infinity. And you would then calculate. So if you wanted to do this numerically, you would now walk up that imaginary axis, and for each point, j omega, where omega is 0.01, now you find the magnitude and angle. Now you go up one more step, and it's j omega 0.02. And you just keep doing that. And we'll do that for maybe 1,000 points on the, no. But that's what you can think of as the Bode plot graphically, and each of these different factors contributing. Each factor now has a magnitude and angle associated with it, and if we just wanted the magnitude of that transfer function, we could just take those lengths and combine them, where the numerator factors are in the numerator and the denominator lengths or factors are in the denominator. And if we wanted the phase, we would do the algebraic sum of those individual angles for the various factors. All of the numerator angles would be added, and we would subtract all of the angles from our poles. Did anyone see something like this in a 320 class? In a 441 class, yes, that's a controls class. You probably have seen it, but this, if it's foreign to you, I want it to start to become a little bit more comfortable to you as far as computing these numbers, these numerical values. How do we, and if you wanted an example, here is one. And now you could go home and play with this transfer function. It's 3 poles and 1 0. And you can see that I spent a lot of time and effort creating those poles and zeros. I simply counted 1, 2, 3, 4. So there's nothing special about that transfer function other than it illustrates that here's a transfer function in pole 0 form, meaning it's fairly clear from each of those factors where your poles are and where your zeros are. What's the order of that transfer function? And the order is determined by the number of poles. Here you have 3 poles, so it's a third order transfer function. How many zeros do you have? Finite zeros. You have 1 finite zero. Has anybody ever talked about zeros at infinity? You have 2 zeros at infinity because you actually have a difference between the number of poles and the number of zeros of 2. That's not so important, but now what's the DC gain of this transfer function? I heard a 4. 4 score, no, 4. Where did 4 come from? Just evaluating h of s when s is equal to 0. And we have 24 divided by 6. And the last time I checked, I think that was 4, wasn't it? 4 times 6 is 24. So this has a DC gain of 4. And it has 3 poles rolling off before a 0 kicks in. And you should be able to sort of visualize or quickly sketch what a Bode plot for this might look like. Those are very close, those poles and zeros, so they're really on top of each other almost, but you sort of have an idea of how you could sketch the Bode plot for that transfer function. What we want to now talk about is how does that carry over into the discrete time case. If you now have a sinusoidal input in a discrete time setting, and you could get that by simply sampling a continuous time sinusoid by replacing t with little n capital T. So now you're just picking off points of this sinusoid. How does that sinusoidal input get changed as it goes through this system, capital H of z? And we're interested in its sinusoidal steady state behavior. The discrete time cosine, let's say, has an amplitude of d and a argument of theta sub 1 n, where you're taking the cosine of something, so that cosine, that argument needs to be an angle, probably in radians. So theta sub 1 is radians per sample, and n is the number of samples. And you can see then that v sub I of n is going to be this oscillating waveform. You inject that into the time domain, into this system, capital H of z, and what pops out? It's very similar to what happened in the continuous time case. That's why we went through the continuous time case. We simply scale the amplitude by finding h somewhere on the unit circle of e to the j theta 1, and we now have an angle that shifts that cosine waveform in time depending on the phase of our transfer function h at that location, e to the j theta 1. Again, once somebody tells you theta sub 1, which you had from the input sinusoid, how fast are they shaking this system, essentially, that now you can use to determine the complex number that you end up with when you evaluate the system transfer function at that location or at that angle on the unit circle. You'll have a magnitude and an angle. And what's the magnitude of e to the j theta? Why am I always, well, I'm getting ahead of myself. Euler tells us how to expand or rewrite e to the j theta in rectangular form. E to the j theta is simply cosine theta plus j sine theta. And if we wanted the magnitude, we take the real part and square it and add that to the square of the imaginary component. So now we have cosine squared plus sine squared. And hopefully you remember from your trigonometry days that that's 1, so the square root of 1 is 1. E to the j theta is always going to have a magnitude of 1. That's why we're playing on the unit circle. If we now evaluate this transfer function at e to the j theta, the distance that complex number e to the j theta is from the origin is 1. And all we have to worry about then is the angle on that unit circle. Where are we at angle-wise? And I'm assuming you've heard the joke. Well, no, I better not say that joke. Joke? So have you heard the joke about Euler or that formula? It was a TV show many years ago, and somebody was on it, and he said, well, I was on the MIT campus. He was a student, and he walked up. This was a gentleman, well, I don't know, a male, and he walks up to a female sitting outside, and he walked up to her, and he said, you must be sine squared. And she goes, what? Yeah, he knows how to communicate, doesn't he? So she goes, I don't understand. He goes, you've got to be sine squared because I'm cosine squared and together we're 1. Anyway, cosine squared plus sine squared is equal to 1. Maybe you'll never forget that. Maybe you can forget the joke, but maybe the joke will remember or remind you of where that comes from. So e to the j theta has a magnitude of 1. I needed to get your attention somehow. Now you're back a little bit, but suppose now somebody gave you a transfer function, h of z, in pole zero form, and they've translated that into x's and o's on the z-plane. That's what I've done here. How many poles are in that transfer function h of z as depicted in this diagram? It's a pretty busy diagram. Can you see how many x's there are? That's not a difficult question, is it? If you can find them. This is like a Where's Waldo, but this is a where are the poles. There's 3. 3 poles, and how many zeros? Finite zeros. 1. So this is now a 3-pole, 1-0 system, and from each pole and from each zero, we can communicate or calculate, compute the length from that pole or 0 to that point, e to the j theta 1, and its angle. What do we turn, or how do we turn from using the positive real line to the right as our reference point, and if we're at the 0, then we're turning up maybe an angle of 50 degrees. Maybe that's theta sub z. What's theta sub p sub 1, roughly? That looks to be bigger than 90 degrees, doesn't it? Do you see how we compute those angles or those phases for each of the factors? And if you were given a certain transfer function and you needed to calculate e to the j theta 1, you could do it by simply measuring the lengths and measuring those angles. So that now h of e to the j theta 1 is some gain scaled by the 0 factor's length and angle and the 3 denominator lengths and angles. Again, if you wanted to compute just the magnitude or the phase, you simply take the product and quotient of those lengths and the algebraic sum of those angles to produce the magnitude and phase of h at e to the j theta 1. That's the theory. Now let's see if we can apply it to a particular example. And now I'm relying on our previous lecture where we had a low-pass filter, and that low-pass filter was a passive low-pass filter consisting of a resistor and a capacitor. And the output of that filter is just the voltage across that capacitor, and the input is across the series combination of the resistor and capacitor. That's our H of S. Or we could write it as a time domain differential equation, and that produces this RC filter. That filter is really just solving this differential equation if I inject V sub I of t and determine what the output voltage V sub 0 of t needs to be for a given time constant determined by the product of the resistor and the capacitor. What's the order of that filter? It's a first order filter. It has one energy storage device. We have one capacitor. Or you could say it's first order because I have a first derivative. I have a V0 prime, or I have a dV0 dt. It's first order, however you want to think about it. And you should, seeing that, know what its Bode plot looks like. And I think last time, didn't we calculate the output in the sinusoidal steady state for a frequency omega 1 of 500, and for that particular low-pass filter we assumed that it possessed a cutoff frequency of 600 radians per second. And we are now exciting that with a sinusoid with a frequency of 500. We inject a sinusoid of a magnitude 2, and we now, after going through that low-pass filter, it now attenuates the amplitude down to 1.54. And if you wanted partial credit on a test or on an interview, somebody said, okay, I inject this cosine or this sine into a filter, what can you immediately write down as the output if that filter is a linear filter? You know its frequency, right? You're shaking that system at some frequency. Well, the output, after the transients have disappeared, the output has to be shaking at that same frequency. So partial credit, you can say, oh, this is a cosine of 500t. And then you could start saying, well, I could find the DC gain of this filter and quickly sketch the Bode plot and say, how close is my actual frequency to the cutoff frequency? If it's quite far away, if it's much lower, then you can say, oh, approximately it's 2 for an amplitude. Here we're pretty close to the cutoff frequency, and the cutoff frequency you're already 3 dB down. So you would be at 0.707 of your starting point, or 1.4 if you were right at the cutoff frequency of 600. So knowing that and seeing a 1.54, you go, okay, that makes sense. And what would your phase shift be if your input was at 600 radians per second as a frequency? What would your phase shift be? Here at 500, we're at minus 40. Would we be closer to 0 or closer to... It'll be 45, won't it? It'll be 500t minus 45 degrees if we are at the cutoff frequency. So this is making sense. We're not quite to the cutoff frequency with our input being at 500, but we're getting close. We're close to 1.4, 500t minus 45 degrees. And that's kind of what you could say without really doing much calculation. I'm somewhere amplitude between 2 and 1.4, and my phase shift is probably getting close to minus 45 because 500 is pretty close to 600. That's what the continuous time low-pass first-order filter produces. for an input cosine of 500. What happens now if we try this with a discrete time filter? And what is a discrete time filter? That's just a linear difference equation. That's pretty easy to build. You can just build this in a spreadsheet. You wouldn't have to go see Josie and find a resistor and a capacitor. Now you can simply go and plug it into a spreadsheet and say, oh, iteratively, this is what I will calculate my output response needs to be if I can just find the difference equation. That's what we want to do now. Can we find a difference equation based on starting with this differential equation? And it's not a very complicated differential equation. It's a first order differential equation. Can we now approximate that to give us a difference equation? Last time I think we started this, didn't we? We said, okay, well, this is known as finding a discrete equivalent. Somebody might hand you a continuous time or a transfer function in the S domain and say, find the discrete equivalent. How can you now translate that into a difference equation or a discrete time filter h of z? How did we go about making this approximation happen? We just had to go back to our calculus, didn't we? Our first semester of calculus. And remember what dV represents and what does dt represent. Those are just small variations of v and small variations of t. And that small variation of t is just the distance in time between one sample and the next, or that's one sample period. And let's just, for notation purposes, say that we'll say it's between n plus 1 and n in terms of that sample. Or we now are saying we have a v sub 0 of n plus 1 sample periods. What is my output voltage at that point in time minus v sub 0 of nt? That's my small change, or that's my dV approximation in the discrete time setting. I'm now just slicing and dicing everything according to this sample period, capital T. That will now be over a consistent dt, which is now n plus 1 times t minus nt. Or I can now, anywhere I had a first derivative in my differential equation, I'm going to replace it with v sub 0 of n plus 1t minus v sub 0 of nt all over. And what happens in the denominator? I distribute that capital T in the first expression across those two pieces, and I have nt plus t minus nt, or the denominator now simplifies to just capital T. And now if you're still with me or paying attention, maybe you're saying, well, what is t? How fast do I sample? I have a first order differential equation. Is there any way that I can find a t other than just pulling one out of the air? So now I want to look at RC, don't I? The time constant, tau. Or we can do it another way, but let's now just say t is our sample period in seconds per sample. And what do we know about the bandwidth of our system? This is connected to RC. What was omega c? What was our bandwidth of the low-pass filter? Do you remember? That was 600, wasn't it? So this was 600 radians per second. How fast are we supposed to sample if that's our frequency of interest in our continuous time system? How fast do we now sample? And now I want you all to be looking at your thumb, right? 30 times faster. That's the rule of thumb, isn't it? So now we have omega sub s 30 times omega c. That's our rule of thumb. So now we have 30 times 600. Or that's 18,000 radians per second. We wanted capital T, and we can find that by realizing that capital T, the sample period, is the reciprocal of the sampling frequency in hertz, and the sampling frequency in hertz is related to the sampling frequency in radians per second by this factor of 2 pi. Omega sub s is 2 pi f sub s, and that's 2 pi over t, so that now if we solve that for capital T, we now have 2 pi over omega sub s. And if we approximate that, we can make pi a little bit smaller. Making t smaller is always erring in the correct direction. So if we now just said, let's just approximate pi with 3, omega sub s was 3, I don't know, how do we want to do this? Over 2 times is that right? Or not? Omega sub s was 18,000, so we can cancel some of these pieces. And t now becomes 1 over 3 times 10 to the minus 3. Or that's 0.333 times 10 to the minus 3 seconds per sample. Now we can convert that differential equation into a difference equation with that particular capital T identified. Where our differential equation was now tau v sub 0 prime of t plus v sub 0 of t equaling v sub I of t. And to convert it, we simply replace that first derivative with that approximation that we just created or said we were okay with. That was now v sub 0 of n plus 1 times t minus v sub 0 of nt all over capital T plus v sub 0 of nt. So really what we're doing is we're sampling, or we're replacing little t with a sampled version, which we're replacing little t with little n capital T. And on the right-hand side, we now have v sub I of nt, where we're using t is equal to nt. we can maybe start to clean this up because we like to have equations for something at time step n plus 1 in terms of other things. Let's multiply all terms by capital T over tau. So that now we have v sub 0 of little n plus 1 times capital T minus v sub 0 of nt. That's coming from the bracketed expression, scaling or multiplying that by capital T over tau, plus capital T over tau v sub 0 of nt equaling capital T over tau v sub I of nt. And let's solve that for the highest indexed sampled output, v sub 0 of n plus 1 times t. We have a 1 on the other side minus capital T over tau, v sub 0 of nt, plus capital T over tau, v sub I of nt. What was tau? Do you remember? That was RC from before, and I think that was previously something like 0.00167 or 1.67 times 10 to the minus 3. Or that's 5 over 3 times 10 to the minus 3. And we know what t is. T was this 0.33 times 10 to the minus 3. Or that's now 1/3. And so now capital T over tau is 1/3 times 10 to the minus 3 over 5/3 times 10 to the minus 3. A lot of things start canceling. That ratio now becomes 1/5 or 0.2. And if we use those or that particular value in the two coefficients on the right-hand side, we see that the scaling factor on v sub 0 is just 1 minus 0.2 or 0.8, so that now we have v sub 0 of n plus 1 capital T is now equal to 0.8 v sub 0 of nt plus 0.2 v sub I of nt. We've now produced a first order difference equation that produces what? What is that supposed to be approximating? What did we start out with, and what did we base this? We had a first order differential equation, and what was that modeling? A low pass filter. So now we have a first order difference equation that produces a low pass filter with a bandwidth of approximately 100 hertz. And now if somebody gave you a generic input signal, V sub I, you could low pass filter it iteratively. you would have to sample that v sub I at what? The sample period every, what was capital T? 0.33 times 10 to the minus 3. So every 0.33 times 10 to the minus 3 seconds, you sample their continuous time waveform. That gives you the v sub I. And if you say, well, I'm not going to initialize my low-pass filter, I'm going to have 0 initial conditions, now you can just iteratively evaluate what your output is going to be if you low-pass filter that time domain waveform signal, v sub I of nt. What would happen if we would actually specify that input to be a sinusoid? So what if v sub I of nt was actually 2 times the cosine of 500? That looks familiar. And now let's replace t with the sampled version, which is little n capital T. But t, remember, was fixed. We can incorporate that into our argument for v sub I of nt, and v sub I of nt is now 2 times the cosine of 0.1667 n, where this 0.1667 is our, call it theta 1. Can we now find the sinusoidal steady state output? We're now injecting this sinusoid, 2 cosine of theta 1n, into this system. You could iterate and find what v sub 0 is for all time if you wanted to, but what if somebody said, well, after the transients have disappeared, what's it going to look like in the steady state? What's v sub 0? What's the output from this low-pass filter going to look like? And if that's the case, what do we need in order to make that happen? If we don't want to iteratively, and you could just plug that v sub I into that difference equation and sit there for a few hours, few days, however long you want to keep crunching and find v sub 0 at each of these sample points. What if you didn't want to calculate all of those points to get to a steady state? What's another approach to finding the output, sinusoidal steady state output? If I gave you the transfer function, could you start doing it? What's h of z? Can you find h of z from what we've done so far? We need the transfer function of the discrete time low-pass filter. And we already know what v sub 0 is in terms of a first-order difference equation. And here I'm suppressing the sample period, capital T, from the argument. We already know that. How do we find a transfer function from a difference equation? Homework 2. So now we can z-transform this. We can z-transform this difference equation and since we're really only interested in the transfer function, we don't have to worry about the initial conditions, where we're going to use the fact that if I wanted the z-transform of, let's say, v sub 0 of n plus 1, what will that be? An advance of 1 in the time domain corresponds to what in the frequency domain? A multiplication by z. So now we have z times the z-transform of the time domain waveform little v sub 0, which is capital V sub 0 of z. What about the z-transform of v sub 0 of n minus 1? Even though it doesn't exist in this difference equation, what would that be? Now we're delaying by 1 sample period in the frequency domain. What we do have is just v naught, and what's its z-transform? That's the easy one, right? That's just v naught of z. If we now apply these relationships to that first order difference equation, we can now say then that we have z times v sub 0 of z equaling 0.8 v sub 0 of z plus 0.2 v sub I of z. And now I can just do a little algebra and end up with the transfer function that I need. V sub 0 of z is now 0.2 divided by z minus 0.8 v sub I of z. There's now my transfer function h of z. And now I can think of this in terms of the block diagram. I have an input being filtered by my system, capital H of z, producing an output. Now, can I draw the pole zero diagram associated with that transfer function? Or what is the pole zero diagram? If I'm interested in the sinusoidal steady state behavior, maybe what I want to do is look at where my poles are and where my zeros are on this transfer function, so that I now have I'm sure I didn't give myself enough room vertically. Can't even count. There's J, and now I take out my compass and I make my unit circle, and I didn't want to damage my screen, so you can see that my compass, I didn't stick the pin down in the origin very well. But you can on your own piece of paper. This is now the z-plane, and my pole is going to be there at 0.8. Where's my 0? I don't have a finite 0. I only have one singularity, and that's that pole at 0.8. And now what do I want to do? If I'm interested in the frequency response, I now want to know what is V sub 0 steady state of n. If my input, V sub I, is now 2 cosine of 0.1667 n. And that's my theta 1. I now have 0.1667 radians per sample, so I'm really just looking at this, converting this maybe so that I can get a visual for this. What is 0.1667? 1/3 divided by 2, or 1/6. And now I can convert that by 180 degrees divided by pi. So that now 6 goes into 180 nicely. That's 30. And pi is about 3. So this is about 10 degrees. If we wanted to do this, it's actually 9.55 if we computed it, but roughly it's 30 over 3, which is 10 degrees. So if you were drawing this on a napkin, 10 degrees is pretty close to 9.55 or 9.6. So that now we need to go up to 10 degrees, wherever 10 degrees would be. And this is now our J theta 1. And how do we use that? What's the structure? Of our sinusoidal steady state response? Do you remember what we had for the theory in the first part of today's class? What's the structure of V sub 0 steady state of n relative to the input? What was our input amplitude? 2. And how does that get adjusted? By h at e to the j theta 1 cosine theta 1 times n plus the phase of h of e to the j theta 1. So now we're letting z equal e to the j theta 1. That's e to the j 0.1667, or what's the magnitude of that complex number? What was that joke? E to the j theta has a magnitude of what? 1. Because cosine squared plus sine squared is 1, isn't it? So now we have a magnitude of 1, and what's the angle? 0.1667 in radians. So now we have an angle of 0.1667 radians. We can use that now to compute or find the complex number h of z when z is equal to e to the j theta 1. That's now 0.2 over e to the j 0.1667, there's z, minus 0.8. Now we can use Euler to rewrite that complex exponential, and now we have 0.2 cosine of 0.1667. And remember, if you're doing this on your calculator, you need to be sure that your argument now is being treated as a radian measure. If it's in degrees, it needed to be 9.55 plus j sine of that same angle minus 0.8. Cosine of 10 degrees, I'm sure you have that memorized. It's 0.9861. Certain things you need to know. That's not necessarily one of them. So the cosine of 9.55 is 0.9861, and the sine of a small angle is about the small angle, so that should be close to 0.166, and it is. Or this now says that we're looking at 0.2 as a complex number. We take 0.9861 and subtract 0.8, and we get 0.18614 plus j 0.1659. Or in polar form, downstairs, we have a magnitude of 0.2493 at an angle of 41.71 degrees. Or that's 0.2 divided by 0.25, which is roughly 0.8, minus 41.71 degrees. And now we have that V sub O, our output in the sinusoidal steady state, is 2 times 0.8, or 1.6 cosine of 0.1667 in minus 41.71 degrees. And that's now our sinusoidal steady state output based on passing this cosine through a first order low pass filter with a bandwidth of about 100 hertz. And hopefully you can see then that if you needed to, you could have pulled out your napkin and measured this all with a ruler and a protractor, because you had, here's 1 and here's 0.8, and here's that point. What was that point? E to the j theta 1. But didn't we just calculate that to be in rectangular form 0.9861 plus j 0.1659? So this point is actually 0.9861 plus j 0.1659. And now I'm sure every period in your trigonometry class you said, when are we ever, or geometry class, you probably said, when are we ever going to use this? And your instructor probably said, February 4th, 2019, in ECE 442, 542, you'll probably use this relationship, which is the hypotenuse of a right triangle. That will give us our length. This length, LP, and this angle, theta p, can be found by just saying, oh, let's use Pythagorean. LP is just the magnitude of 0.9861 minus 0.8. That's the horizontal distance. And the vertical distance is 0.1659. And we calculated that to be 0.2493. And the angle, theta sub p, is just the angle that has a tangent with a vertical distance of 0.1659 and a horizontal length, again, of this 0.9861 minus 0.8, or 41.72 degrees. Questions on that example or that exercise? Could you now do this on your own? If somebody gave you, what would they need to give you? Or if they now handed you a first-order differential equation, could you now find a difference equation for that? Question?
So when you did the z-transform to find the transfer function, you neglected initial conditions?
Yes, so the question was when I took the transfer function, or I'm sorry, when I took the z-transform of the first order difference equation somewhere right here, I neglected the initial conditions. I didn't worry about v sub 0 at any particular time because I'm really worried about the dynamic behavior of that filter and not a specific solution.
So if you were to take into account the initial conditions, that would have like...
So now if I were to take into account the initial conditions in this z-transform, that would be sort of begging the idea that, oh, you're trying to find the complete solution to this difference equation when it's excited by a given input, v sub I, with these specific initial conditions. And then you could find the complete solution to that question if somebody wanted to incorporate the initial conditions. We don't need to do that for the analysis we were performing. We were interested in the sinusoidal steady state, which means we're allowing all the transients to disappear.
So we would have like a plus bunch of other terms if...
So we would have some other constants incorporated into that z-transform expression when we account for the initial condition. Just like when you take the Laplace transform of a derivative, you have s times v sub 0 of s minus v sub 0 at t equals 0 minus. Other questions on this example? If I now, well, I think that's probably enough, and what we will do is we will pick up with region of convergence for question? Pardon? So the very first step in converting or finding this discrete equivalent, I introduced some error. There's going to be some error between the time domain or the continuous time solution versus the discrete time, but that error is probably very minimal in terms of what you would see in reality if you actually implemented this difference equation form of a low-pass filter versus implementing it with hardware. Your hardware might have more error because you don't find an R and a C value exactly like you wanted. So it's really just how do you want to approximate that derivative? And we did it with a first order approximation or a forward-looking approximation, and we'll look at other ways of approximating derivatives or integrals later in the class. We'll look at other ways of doing discrete equivalence. So the error is somewhat based on the sample period capital T, but it's also how we looked at it. We said this is now a forward-looking approximation to our derivative. So we'll look at other ways of approximate or going between continuous time and discrete time later in the semester. Other questions? We'll call that good for material for exam number 1, and we'll pick up with new material following exam number 1.